Hello everyone, this is Laura Ferranti. I'm an assistant professor in the Department of Cognitive Robotics at Delft University of Technology. There I coordinate the Reliable Robot Control Lab. And today, together with my colleagues from the Cognitive Robotics Department, Bas van der Heijden and Jelle Laux, we will present how to benefit from learning in predictive control, and we will introduce our new toolkit, Eager, that facilitates the use of learning for robot control and motion planning. Autonomous robots, such as self-driving cars, autonomous vessels, robot manipulators, and drones, will soon be part of our daily lives. These robots will help us in our daily activities, such as commuting to work or producing goods. These robots, however, will require complex algorithms to help them navigate, for example, in our cities or in a factory. In this context, algorithms that allow the robots to plan safe trajectories around humans or other robots play a fundamental role. These algorithms act as a bridge between how the robot perceives the environment and how it reacts to it. Motion planning and control algorithms need to fully exploit the information coming from the sensors and the computer vision module, of course, to understand the environment and avoid collisions by sending the appropriate commands to the robot itself. There are, of course, several ways of approaching the problem of robot motion planning and control, but in this talk I want to focus on a special algorithm that is called model predictive control that can be used for both local motion planning and control. In this context, after a very short introduction about MPC, we will show also a couple of examples on how we can connect such a technique with learning-based approaches based on our experience at TU Delft. As I mentioned, this talk focuses on a specific technique for robot motion planning and control, that is MPC. From a mathematical point of view, MPC is nothing more than a constrained optimization problem. You can specify the robot navigation objectives and the navigation envelope. And then the MPC controller will look over a predefined time window that we call prediction horizon on how to optimize the desired navigation objectives by accounting for the constraints described in the navigation envelope. These constraints include the robot model and the robot actuator limitations. And in case we are using MPC for robot motion planning, you can also specify in the navigation envelope the information that you may know concerning the obstacles surrounding the robot. This was just to give you an idea of what MPC is about, and I hope you will be more interested in this technique and you can look it up online, or you can send me an email to ask for more details. Now I want to focus more on how learning can help model predictive control for robot navigation, and for this I will use a couple of examples of work that we did in the Cognitive Robotics Department at TU Delft. The first example that I wanted to show you concerns the design of an MPC-based local motion planner for autonomous cars. As you can imagine, in the future, autonomous cars will have to face scenarios like the one you see here in the video. These vehicles will be equipped with several sensors that can gather information from the environment, and a perception module able to infer the intentions of, for instance, of the pedestrians. The MPC planner, in this case, will have the task to use such information concerning the behavior of the surrounding pedestrians, which comes, of course, with uncertainties, and plan safe collision-free paths. In this context, the challenge is how we can design a local MPC planner that can fully exploit the information that comes from such a perception module by keeping into account the uncertain behavior of the pedestrians to avoid collisions. Given that the perception module will provide the future intentions of the pedestrians with some uncertainties, from a more formal point of view, we can express the collision avoidance constraints in the MPC formulation as probabilistic constraints on the position of the vehicle and of the pedestrians. These constraints are called chance constraints and allow our MPC planner to consider the risk of collision in the calculation of the path for the autonomous car. In this case, we bound the risk of collision at every stage of the planned path of the vehicle, as you can read here from the slide. Ideally, we would like to solve the chance-constrained navigation problem. This, unfortunately, is not possible in real-time applications. So, we rely on a reformulation of the problem that is based on a so-called scenario theory. Without giving too many details here, and if you're interested, please refer to the paper indicated on the slide, the idea is the following. So what we do is that we sample from the uncertainty set provided by the perception module, and by using these samples, we are able to rewrite the probabilistic constraints in this chance constraint problem as a set of deterministic constraints as defined in the scenario program on the slide. The figure on the top right part of the slide should give you also an idea of how this reformulation is obtained, starting from the uncertainty set indicated in red and identified by the perception module. Loosely speaking, it is as if we pretend to have multiple pedestrians close to each other at exact positions rather than one pedestrian with an unbounded uncertainty on his location. So here I wanted to show you an example on how the proposed methods works in a crowded environment. You see on the left-hand side of the slide the proposed approach, and on the right-hand side an MPC baseline. The MPC planned path is represented in blue in both cases, while the current position of the robot is highlighted in black, and the trajectories of the pedestrians predicted by a perception module are highlighted in light red, while their current positions are highlighted in solid red. You can see from the video that the robustness of the proposed method towards the uncertainties in the behavior of the pedestrians results in a much more agile and efficient navigation of the robot in such a crowded environment compared to the baseline. So in this work, learning is not directly used in the MPC formulation, but it's a very nice example on how we can benefit from learning in the motion planner of an autonomous robot, and in particular how we can exploit the information coming from a learning-based module to navigate the robot in a dynamic environment. And next, Bas will tell you more on how to directly use learning to simplify the definition of the model predictive control problem for robot control.
Prior works have shown that reinforcement learning algorithms can learn complex policies directly from raw images. Unfortunately, these algorithms often require a lot of experience to learn these policies. Hence, prior methods for data-efficient learning typically use representation learning to obtain a smaller vectored latent representation that is better suited for reinforcement learning. However, such methods are task agnostic. The models represent all dynamic elements they observe in the world, whether they are relevant to the task or not. And the issue of distractions may be less evident in highly structured lab environments, since any change captured by a camera is likely task relevant and thus worth representing. By contrast, visual images that autonomous cars observe contain predominantly task irrelevant information like moving trees. To illustrate this, if a representation is naively learned with full observation reconstruction, the two images on top may have different encodings. Then, a reinforcement learning algorithm could potentially behave differently given either observations, due to their different encoding, even though their relevant details were equal. This means the RL agent gets distracted by irrelevant dynamics. Hence, we propose an efficient model-based reinforcement learning method called Deep Cocoa that targets robotic applications with the listed characteristics. It operates in the usual reinforcement learning setting, but uses pixel image observations that are distorted with task-irrelevant dynamics. In this case, we add other distractor pendula not controlled by the agent to the pixel image to distort it. We use these observations to learn a Koopman representation with a deep autoencoder architecture. This representation is task relevant because we only reconstruct observed costs rather than the full pixel observations. And the learned Koopman representation and quadratic cost model, together with several mild assumptions, enabled us to apply linear model predictive control, which is a convex control technique that can be solved efficiently every time step. We compare the learning performance with two state-of-the-art methods in two scenarios. First in a standard clean scenario, and then in the distractor scenario I previously described. We see that the baseline methods quickly learn in the clean setting, but fail to learn anything in the distractor scenario. In contrast, Deep Cocoa is able to learn a successful policy in the face of distractor dynamics. In summary, Deep Cocoa learns a Koopman representation that is task relevant by only reconstructing observed costs rather than full observations. Furthermore, the representation is compatible with efficient control algorithms such that the computational load only scales linearly with the latent state dimension. And the Koopman representation that is learned does not make limiting assumptions, such as linearity between actions and latent states, nor does it require a priori knowledge of the problem. Finally, we have demonstrated that the efficient representation allows direct control with high-dimensional pixel images. So, it is clear that we can benefit from learning in control applications. However, learning in the real world is still impractical for various reasons. Firstly, directly learning with a physical robot can lead to dangerous situations. And, as alluded on before, reinforcement learning agents are generally not very sample efficient, so training can take a long time. Finally, as most reinforcement learning agents train in an episodic setting, simple resets of the environment can already become quite challenging. There do exist strategies to mitigate these challenges, such as adding a safety layer, using domain knowledge to jumpstart training, or set up a simulator for faster than real-time training. Unfortunately, these strategies are often implemented on an ad hoc basis. For example, many roboticists spend a significant amount of time to set up the right simulator, only to find themselves re-implementing their code as the real robot has a different interface, modified by the safety layer. Therefore, we started developing a new framework called EAGER, or Engine Agnostic Gym Environments for Robotics in full. And it's a toolkit for simulated and real robot training, and we plan to release this toolkit by the end of this year. EAGER enables the user to define new tasks in environments that can easily be composed with various robots and sensors without requiring extensive programming. Also, EAGER allows the user to seamlessly switch from simulation to a real robot by being agnostic to the physics engine. Moreover, EAGER contains important features for roboticists to perform real-world learning, such as a safety layer. And the defined environment follows the OpenAI Gym interface, so we can plug in algorithms from existing toolkits, such as stable baselines, to solve the task afterwards. To make the previous specifications more concrete, we would like to target the following use cases that are not yet all supported in existing toolkits. For example, how to deal with an environment reset in the real world where you can't simply call a reset function as you would do in simulation. And as mentioned before, how can we recompose environments without extensive reprogramming? And can we speed up learning by fusing simulated and real-world experience? Also, how can we kickstart learning by easily integrating pre-trained perception modules? And then, as alluded on before, how can we add a safety layer that checks and overrules unsafe actions commanded by the reinforcement learning agent? And finally, how can we achieve faster than real-time training without jeopardizing the simulated accuracy? To illustrate how Eager works, Jelle Luijks will now give a coding demonstration that shows how the framework attempts to deal with some of the aforementioned use cases.
In this demo, I will show you how to create a simple environment in Eager consisting of a robot, the VX300S, and a RealSense D435 camera. Throughout the demo, I will show you how to create a simulated environment for this robot, and later we will use this same environment on the real robot. Going through this Hello World example, we hope to show you the core features and functionalities that Eager provides. Before creating the environment, we performed an extrinsic calibration routine to obtain the position and orientation of the camera with respect to the robot base frame. Later, we will use this location and orientation to create a simulated version of our real setup. After calibration, we are ready to create the environment. We start with a skeleton file, in which we take actions in a yet to be created environment and obtain observations and rewards. This will probably be familiar to you if you have worked with standard OpenAI Gym environments. First, we will create an engine, in this case a PyBullet engine, since we are going to simulate the robot in PyBullet. Next, we will create the robot. Creating a robot is just as a single line of code with the object.create method. Next, we create the camera, again with the object.create function. For the camera, we also specify the position and orientation, which we obtained from the calibration routine. Thanks to the compositional nature of the toolkit, we can easily add multiple objects to a single environment. Now we are ready to construct the environment. We do this by specifying a name, providing it with the engine and a list of objects. Also, we will use the images of the RealSense camera for rendering. If we run the file, we see the VX300S and RealSense camera in the PyBullet simulator, and we see that it is performing random actions. However, before going to the real robot, we need to add processing to the actions, since currently they are not safe. In this case, we add a processing step that ensures that the actions obey a velocity limit and that the robot does not move lower than a specified height. Running the file again shows that the actions are now slower and that the robot is not going through the ground anymore. We are now ready to go to the real robot. Since the environment is engine agnostic, the only thing we need to do is change the engine from PyBullet engine to the real engine. Now we see a similar render as in PyBullet, but now from the real camera images and with the real robot. This showcases the ease with which one can switch between engines, in this case from a simulation in PyBullet to the real world. So far we have created 4 engines, one for PyBullet, the real world, Gazebo and Weebots. In the following example, we show a similar environment, now in Weebots, with 2 Euro 5Es and a multisense camera. This example showcases that since Eager is based on composition, it is easy to create environments with multiple different objects.
I hope that after this preview you will be interested in using and testing Eager for your research as soon as it will be available at the end of 2021. Thank you Bas and Jalle for your presentation and thank you all for the attention.